Hi and welcome. My name is Stefan Johansson. I'm an engineer at Oracle, working on OpenJDK and garbage collection. I've been doing so for the 8 past years, and today we're going to talk about G1, the default garbage collector in OpenJDK. Let's take a look at today's agenda. So we're going to start off with talking a bit about GC in general in OpenJDK, then dig in a bit more to G1, and then focus mostly on the progress made in G1 since JDK 8. At the end, we'll take a very quick look at the future. My main goal with this presentation is to show you all the good things we've done with G1 since JDK 8 and hopefully encourage some of you to move to a newer JDK. So let's start off with GC in general. GC is not all about reclaiming memory. We actually also need to hand out the memory to be able to then reclaim it. And having fast allocation is done more or less the same regardless of the garbage collector you use in OpenJDK. So we're using something that we call TLABs, Thread Local Allocation Buffers, that are requested by the Java threads. The Java threads can then allocate objects by just bumping a pointer and filling out the object. Once a TLAB is full, the Java thread then requests a new one. Once the GC can't satisfy a request for new TLABs, they have to do a garbage collection. And this is the thing that differs between the available collectors. They all want to serve different use cases. That's why we have many of them. When you design a GC algorithm, there are a few different strategies, or there are quite many strategies, but I'm going to mention a few of them. In OpenJDK, all the GCs are what we call tracing. This basically means that we start off with a well-known set of routes, and from those routes we follow the references to other objects until we don't see any new references. This way we learn which objects are live and which objects are not, so we can then collect the garbage. So there is no reference counting or anything like that to determine liveness in OpenJDK. Another thing you want to consider is if you want to do the collection work stopping the world in a GC pause, or if you want to do it concurrently while the Java threads are still running. And you also want to decide whether or not your GC should be generational. If a GC is generational, the heap is divided into one or more generations. In OpenJDK, we only have 2 generations for the generational GCs. We have the young generation and we have the old generation. All new objects are allocated in the new generation, and then after a few GCs, if the object survives, they are moved to the old generation. Eventually, the old generation will be full and will also have to be collected, but that's something that happens way more seldom. You also need to decide what focus your GC should have. Should it aim to have really good throughput, very low latency, or minimal footprint? To better explain those, throughput is mainly the number of transactions you can complete in a set amount of time, while latency is the time it takes to complete one transaction. And with footprint, we basically mean the overhead caused by the GC algorithm, so additional memory used or additional CPU resources. Currently we have 5 supported collectors in OpenJDK. I'm not going to talk about them all. Today, as I mentioned, we're going to focus on G1, the default collector currently. The old default collector Parallel was focusing on throughput. It had good average latencies, but the worst case latencies when collecting the old generation were quite bad. So that's why we switched over to G1, which have a more balanced performance. And now let's take a closer look at G1. So as I mentioned, the basic idea here with G1 is to have a balance between latency and throughput. And the 2 main attributes to achieve this is that G1 is region-based. This means that G1 divides the heap into fixed amount of regions with a fixed size. These regions then belong either to the young generation or to the old generation. To be able to get good latency, not having to do collections of the whole heap, we also need something that we call concurrent marking. This is gathering liveness information for the old generation concurrently with the Java threads still running. So we're able to determine what's live in the old generation without having to stop the Java application. Once we have this liveness information, we can do something we call mixed collections. So this is collecting both the young generation but also some old regions. This way we can split up the work of collecting the old generation, so we don't have to take the hit to collect it all at once. This is also a way to avoid very costly full collections, which can still happen with G1, but we really try to avoid them. We also focus on making G1 easy to tune. So apart from setting your preferred heap size, the main tuning knob that you should use is the pause time target. The default value for this is 200 milliseconds, and if you want to improve your latency, you should turn this down, and vice versa. If you focus on throughput, you can turn this value up. Some current status for G1. G1 was added in OpenJDK in JDK 6, but it didn't get support until JDK 7 U4. Then we put in a lot of work in the JDK 8 timeframe to really make G1 stable and mature, added some really necessary features. This made us take the decision to make G1 the default garbage collector in JDK 9. Since then, it's still actively maintained and has improved even more. And yeah, this is what I'm going to focus on for the rest of this presentation. The progress that we've made since JDK 8. Let's start with a quick overview here. We've done more than 1,000 enhancements to G1 since JDK 8. It's some very big features and some really small cleanups, but yeah, a whole lot of things have been done to significantly improve the performance. And we managed to improve it across all areas. So we improved the throughput, the latency, and the footprint. And one way we've been able to do this is that we've reevaluated some of the old design decisions that were made with G1. And by redoing this in a better way, we've been able to cut away some of the old trade-offs that we had to do in G1. So let's start off with throughput when looking a bit closer at what we've done. So one of the big things here is that we've improved the NUMA awareness for G1. This means that if you're on a big system with a lot of NUMA nodes, G1 will perform better by making sure that the allocations are done on a NUMA node local to where the Java thread is running. This has proven to give very good performance boost on large NUMA systems. Another thing that we've done is that we've focused a lot on making sure that the concurrent work, for example concurrent marking, is very efficient in G1. And also that we only start the concurrent marking when it's actually needed. So we made sure that we postpone it as much as possible, and also made it possible to abort the concurrent marking if we realize that we don't have to do it anymore. Another important feature that we added is the parallel full collection for G1. As I mentioned, G1 tries to avoid the full collection at more or less any cost, but in some use cases there has to be full collections. And having a parallel version of this really helps to avoid really bad worst case latencies and improve the overall throughput quite a bit. So let's take a look at some numbers when it comes to throughput. Here I'm using a benchmark that's called SpecJBB 2015. When you do a compliant run of this benchmark, you get two metrics out of it. One that is raw throughput and one that is throughput with latency requirements. The measurement we're looking at here is the raw throughput one. I've been running with a 16 GB of heap, more or less without any tuning, just setting the heap size, making sure NUMA is used in large pages, but nothing of tuning the collectors themselves. I included parallel in JDK 8 since parallel was the default back then. But then for JDK 11 and 17 I only have G1 numbers since that's the default in those releases. As you can see, back in JDK 8 parallel was better than G1, but with JDK 11 and 17 G1 has been able to move past parallel. Parallel is still better in JDK 11 and 17 compared to parallel in 8, but not as good as G1, not for this benchmark at least. To be fair, these scores are not only improved by the things we've done in GC. This is a very general Java benchmark, so all the improvements made to the Java platform contributes to these throughput scores. So let's head over to latency. When it comes to latency, when you want to improve that, you basically want to make sure that the pauses are as short as possible, and also that you have predictable pauses so that you keep the pause time prediction or the pause time goal set by the user. To shorten the pauses, we really focus on improving the parallelism in the pauses, making sure that even the smallest phases can be scaled up to use multiple threads if needed. We also made sure that the processing itself is very efficient. This is true for everything from the internal processing of G1 data structures to processing Java-lang references. To make the predictions better, we focused quite a bit on taking samples and making sure we handle them the correct way, so that we make sure that we can schedule the pauses in time to be able to complete them within the pause time target set by the user. Another thing that helps us to achieve this is what we call abortable mixed collections, which is a way to shorten the mixed collections by being able to abort them if we realize that they take too much time. Yeah, let's see how this has improved when it comes to the latency score, or the throughput score with latency requirements from SpecJBB. As you can see here, the improvements are quite significant. Compared to JDK 8, the score we get with JDK 17 is almost 50% better. And yeah, this is more or less, or this is at least heavily impacted by the improvements we've done with G1 in the GC, because most of the latency in the Java platform comes from GC pauses. Another cool thing here is that we can trade some throughput for even better latencies. So the bar to the right here, JDK 17 at 50 milliseconds, is when I set the pause time target to 50 milliseconds instead of the default of 200. That way we're able to push up the latency score even more. To be fair, this comes with a throughput hit, so the throughput score is a little bit worse when setting this value. But it all depends what you're focusing on. As I mentioned, these scores are heavily impacted by the GC pause times, so let's take a closer look at the average and P99 pause times for the G1 collector in JDK 8, 11 and 17. Here I'm also using SpecJBB 2015, but not the compliant run. Since that is done with a varying load, it's not fair to do a pause time comparison. But instead I'm running the same benchmark with a fixed load at around 60% of the maximum load that we can handle. And as you can see, in JDK 8, the pause times are below the pause time target of 200 milliseconds, both the average and the P99. But the progress that has been made since then is quite impressive. In JDK 17, the average pause time is down to 84 milliseconds, and the P99 pause time is at 111 milliseconds, which is really great. If we want to push this down even more by setting the pause time target to 50 milliseconds, we get something like this. And as you can see, the average pause is below 50 milliseconds, but not the P99 score. So when pushing the latency down this far, we still have work to do to be able to push the P99 pauses within the pause time target. When talking about low latency, one has to mention our new low latency collector developed at Oracle, ZGC. So here's a bonus slide. The main goal, or at least one of the main goals of ZGC, is to provide sub-millisecond pauses. And with JDK 17, this is achieved for a lot of benchmark. And in this case, as you can see, both the average and P99 pause time is way below 1 millisecond. And I can assure you that the maximum pause time is also below 1 millisecond, but I didn't include it here in this slide. To be able to achieve this, ZGC does all the heavy work outside the GC pause. So basically everything from scanning the thread stacks to doing the compaction is done while the Java threads are still running. So yeah, if all you care about is low latency, you should really go check ZGC out. The last thing I want to talk about today is footprint, and footprint from a memory perspective. This was something that we heard many complaints about when it came to G1 back in the JDK 8 timeframe. Especially complaints that the remember set took up way too much space. You might ask yourself, what are remember sets? And it's a fair question. The simple answer is that they are the internal data structures in G1 that we need to be able to collect regions. So young regions always need to have remember sets, while old regions only need to have remember sets when we are in a phase of collecting old regions, so in a mixed phase. Before JDK 11, we kept the remember set around for all regions at all times and kept them up to date. This was very costly, both when coming to processing time, but especially from a memory perspective. So what we did in JDK 11 was to add a feature called rebuild remember sets concurrently. So after the concurrent cycle, before doing the mixed collections that needs the remember sets, we rebuilt the needed remember sets for the old regions. This proved to be a really big win when it comes to memory savings. Since then, we worked hard to improve this even more, making sure that we size the remember sets the correct way and making sure that we only keep the old region remember sets that we actually will need. We also spent some time making sure that G1 can return heap memory to the OS in a better way. Prior to JDK 12, G1 could only return heap memory after a full collection. And as you might remember, G1 tries to avoid full collection more or less at any cost. So yeah, basically before JDK 12, we didn't return memory very much. In JDK 12, we added support to shrink the heap and return memory after the concurrent cycle as well. This, together with the feature to periodically schedule concurrent collections, makes it possible for G1 to behave really well in memory constrained environments. But now let's take a look at what the remember set work has given on in terms of memory savings, or maybe not savings, but at least not spending way too much memory. Here I'm using a stress test that we call the Big ROM tester. It basically mimics an in-memory database or cache, which does reads and writes and deletes. This is a very good way to stress the remember set implementation in G1 because it forces a lot of updates in the old generation. Here I'm running with a 16 GB heap, and the graph you see here shows the additional memory usage used by G1 to be able to handle this 16 GB heap. So as you can see, back in JDK 8, we actually needed almost 5 GB of additional native memory just for the remember sets and some other internal GC data structures to be able to manage this test. With rebuild remember sets concurrently, we were able to push this down to around 3 GB in JDK 11, which is a really good improvement, but it's still quite a bit of an overhead. So all the work we've done since then with trying to shave away even more, making sure that the remember sets are correctly sized and that we only keep them around when we actually need them, has proven to be very successful. So now we've been able to push the overhead down to around 1.5 GB. And the 10% overhead, that's kind of acceptable. And parts of this is not only the remember sets, but other parts that that will be really hard to optimize away. Cool, that's it for the progress. A quick glimpse at what lies ahead. So we want to keep improving G1, of course. It's everything from usability improvements to make sure G1 behaves good in the cloud. We want to continue to improve the throughput. One way to do that is to improve our write barriers, because we know that those are a bit more costly than, for example, for parallel. So we're investigating that. And again, we want to do even further footprint reductions. And for JDK 18, we already have some things lined up. So we know that we are able to improve this even more. So to finish this off, what's the key takeaway from this presentation? Well, the main thing here, there have been massive improvements to G1 and to the Java platform since JDK 8. So if you're running an older JDK, I really encourage you to try JDK 17. It's just released and it comes with a lot of good features and really good performance. If you're using a different collector than G1, I certainly think you should try G1 out. It's improved quite a bit over the last few years, so if you had bad experience in the past, you should try it out again. Also, going forward, we have a lot of exciting features lined up in the pipe, and this is how we're going to bring G1 to infinity and beyond. Thanks. That's all from me today.